Good evening, and welcome to the first of two videos on Chapter 3, Sensation and Perception. All right. Um, this section, or the third section of Chapter 3, is entitled How We Make Sense of What We See. Now, we've said before that of all of the senses that human beings possess, most definitely the one that we rely on the most is our vision. All right. And so what this section talks about is how our eyes and our brain, mostly our brain, but how everything works together to make sense of the things that we see. Our eyes are only input tools. They can send images to our brain, but it's our brain itself that actually perceives this. The second part of this video will be a lot of fun because there we'll look at some optical illusions and see exactly why we perceive them the way that we do. All right. So, in order to talk about this, we're going to go right back to the founding principles of Chapter 3, and those are sensation and perception. All right. In order to make sense of the things that we see, we need to do both. And although this slide kind of indicates that they are separate but maybe equal, in reality, sensation and perception have to occur together. They have to work together. If one is not occurring, then the other can't occur either. And we'll get into some examples of that as well. So, what exactly are sensation and perception? Well, sensation, as you can see by the definition here, is the initial information uh, gathering and recoding by the sensory structures. And so, what that means is as light enters the eye, it is gathered by the retina. All right. And we talked a little bit about how that occurs. It goes through the ganglion and the bipolar cells and strikes the sensory receptors, blah, 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 the rods and the cones and all that nonsense. And then a signal is sent by the optic nerve into the brain. And the brain then recodes that information, right? Because it starts out as a stimulus of light, but it's recoded into an electrical signal in the neurons as it travels up to the brain. The second portion here is probably the most important, and that is perception, because this is the interpretation by the brain of sensory information. So, as the signals are sent from the eyes to the optic nerve, or through the optic nerve into the brain then has to make sense of them, and that is what we call perception. All right. Um, the light rays that strike our eyes are being sensed, but the image that we form based on that information is our perception. All right. So sensation and perception are the two most important principles of how we make sense of what we see. Now, this occurs both from what we call the bottom up and from the top down. So, bottom-up processing is the processing of incoming sensory information as it travels up from the sensory structures to the brain. So, in other words, these again are the light rays. This is the sensation aspect of this, as
It's
you will.
9 o'clock.
Well, thank you, Jesus. And so we send information from the rods and the cones through the optic nerve and into the brain. And as it travels through that nerve and into the brain, it's processed. The information is processed. We take in information about how bright the light is, what colors are present in it, maybe the potential shape of the image that we happen to be looking at. All right. But that's all information that's sent from our eyes to the brain, and that's bottom up processing. On the other hand, top down processing is using the brain's knowledge, our beliefs, and our expectations to interpret sensory information. All right. We base our perception on previous knowledge. All right. We expect to see something. All right. I expect that when I walk into my house, that my couch is going to be over there and my The dog's crate is going to be over here, and the TV's in that corner, and that sort of thing. All right. If I walked into my house and it was not like that because my knucklehead triplets had decided to rearrange the furniture, that would immediately cause my perception to be way off, and I'd be very confused, at least for a minute, and then I'd have to kill some children. But that's neither here nor there. A good example of the difference between bottom up and top down processing comes from from an example of sound. All right. So, for example, if you listen to someone speaking a foreign language, all right, bottom up processing allows you to hear the sounds. You hear the noise. You hear the words of this. Somebody comes in and speaks, Italian or Chinese or some language other than English or whatever your native tongue happens to be, and you hear the sounds. You definitely sense them, and that's bottom up processing. However, because you don't know what those words mean, right, you can't interpret them. There's no top-down processing. You can't use the information that's already stored in your brain in order to figure out what in the name of God the person is actually saying. All right, this is what infants, babies, oftentimes have difficulty doing. If you've ever seen a 1 or 2-year-old toddler talking, they babble up a storm, all right? And their parents have no idea what they're saying half the time, right? They know what they're talking about, but nobody else does. All right. Now, by far, the most important aspect of processing for humans is top-down processing, because this is what's occurring in the brain. This is really the perception, if you will. And it starts with what we call the perceptual set. All right. And what that means is the interpretation of ambiguous sensory information in terms of how our past experiences have set us to perceive it. All right. So, examples of this. All right. If you are watching a baseball game, all right, let's say, oh, I don't know, the Mets are playing the Red Sox as they are right now on it's July 30th. Mets are losing. But anyway, you see a close play at first base, and you're immediately going to say safe because that's what you want it to be. Okay. You're going to call or make the call that favors your team, whether it's right or not. Okay. And of course, you don't want to see the Red Sox win. So, you want the play to go in your favor. Another aspect of top-down processing is what we call contextual effect. And this is the use of the present context of sensory information to determine its meaning. And a great example of this comes right out of your textbook. All right. If you look at the characters IV, all right, here, all right, they can mean different things in different contexts. So if you read the sentence, Jim was in the hospital and hooked up to an IV. All right. So there you're using those two symbols as letters. All right. And it stands for intravenous, right? When you're hooked up to a solution of saline or medication or whatever it happens to be. Hopefully none of you have ever experienced that and won't. But IV means something very specific. However, if you look at those same two symbols that come after a name, like Edward IV was the King of England in the 15th century. Well, those symbols now represent Roman numerals, and IV represents the Roman numeral 4. So that sentence actually reads, Edward IV was the King of England in the 15th century. Okay. I think he was the one that fought Braveheart, if you've ever seen that movie. So it might have been the third. I don't know for sure. Anyway, but again, when you read the first sentence, you're looking at those symbols as letters, I and V. When you read the second sentence, you're looking at them as a Roman numeral. All right, 4. Okay, so look at the picture that you see that's on the right side of the screen right now. What do you see? Do you see a pair of faces? Or do you see a vase or maybe a short table? Depending upon how you perceive the image, you can see both things. If you concentrate on the blue, you'll see the faces of, I think it's two women looking at each other. All right. Do you see that? However, if you concentrate mostly on the center of the picture, you see a vase or a table or maybe a weird looking cup, for example. All right. Now, what this is part of what we call the figure and ground principle. And this is part of what's known as Gestalt psychology. The Gestalt group were a bunch of German psychologists in the late 1800s who were looking at the difference between the foreground and the background in images and that sort of thing. And what they said was essentially, for this figure and ground principle anyway, was that it is an organizational principle where the brain organizes sensory information into a figure or figures, whatever's at the center of attention, and the ground, which is the less distinct background. Now you can see the image here both ways because this is a reverse figure. In other words, you can see it both ways. If you concentrate on the blue, you see the two faces. If you concentrate on the white, you see the table or vase or cup or whatever it is in the middle here. All right, and so it depends on this organization. It depends on what you are viewing as the figure and what you are viewing as the background or the ground in this case. All right. So, and this is a very famous example of this sort of thing. And there's other images like this out there. Okay. Now, in terms of this kind of thing, there's actually lots of other very famous images here. Excuse me. This one is another very famous one. All right. And again, the words on this slide are the same as the words on the other one. But have a look at this image. What do you see? Do you see a beautiful young woman looking away from you? All right, looking back into the slide, say, so to speak? Or do you see an old woman who's kind of looking toward the left-hand side of the screen? Well, if you look here, oops, come on. Look at this part right here. This is the chin and jawbone of that beautiful young woman. Okay. And so up here, this would be her eyelashes. Here's her hair and maybe some kind of hood and a fancy coat, fur coat maybe that she's wearing. She's got some kind of little feather sticking out here. On the other hand, if you see the old woman, this is her big knobby nose. Here's her mouth. Here's her chin. Here's her eye. All right, this is a mop of hair covering her forehead, and there's a big white hood covering her there. All right, and so this again is a figure and ground image because you can see it two ways depending upon what you see in the foreground and what you see in the background. All right, the figure and the ground. All right. Now, there's a couple of other aspects to this that you should be aware of. All right. Two more Gestalt principles, if you will. They are closure and subjective contour. Now, closure is the perceptual organizational principle that the brain completes or closes incomplete figures to form meaningful objects. All right. This occurs actually all the time in what we call our blind spots. If you ever did this experiment in your high school biology class or maybe even a psychology class, you hold a dot on a piece of paper right in front of one of your eyes, and you move it back and forth slowly, and and keep the eye closed, and all of a sudden the dot disappears because there's a blind spot in each eye, and yet the other eye makes up for it, and your brain processes this and knows what to fill in to make that a meaningful image to you. A very similar concept is what we call a subjective contour. This is a line or a shape that is perceived to be present but does not really exist. The brain creates it during perception. All right. And there's some very great examples of this, but things that aren't really there that simply appear to be there, even though we know that they're really not. All right. I'll give you an excellent example of that in this. This is called the Kawasaki, I think. Kind of like the motorcycle. I might be wrong. It's a long Japanese name, but this image here, and when I scanned it into the computer, it blurred a little bit on the right-hand side. But if you look at it very carefully, can you see the bright white triangle that's laid over the other triangle? It's not really there. All right. Up here, damn it. Up here, you've got a little shape that looks like a Pac-Man, and another one down here, and another one down here, right? And this is the mouth of Pac-Man. This symbol is just a caret, all right, like you would use on the typewriter. It sits right above the number 6 on your keyboard. The triangle that you see here does not exist. It's not really there. Right? It just appears to be there. It seems to be there because of the way that the picture is drawn. All right. And so this is an example of subjective contour. Okay. Now, the next concept, perceptual constancy. This is the perceptual stability of the size, shape, brightness, and color of familiar objects seen at varying distances, at different angles, and under different lighting conditions. If you see a lion, okay, and under bright light and at a certain distance, you see this shape. It looks like a kitty cat, and it's tan. All right, but as the sun goes down, it appears to become gray in color. But your brain realizes that lions are tan, and therefore you see the lion as tan. That's your perceptual constancy. Right, even though there's not enough light to see it as tan in color, you still know that it's tan in color. All right. The same thing is true for objects at different distances, at different angles, under different lighting conditions, and so on. All right, your brain is able to actually take into account distance and light and angle and all of those things, and still make sense of what you are seeing. Okay, and that is perceptual constancy. Okay. Now, the last thing that I want to talk about in this video today is what we call depth perception. And this is our ability to perceive the distance of objects from us. All right. We can tell how far an object is away from us because of a variety of different cues that contribute to our depth perception. All right. And this is true even if you have one eye closed. All right. A lot of people think that you can only perceive depth if you've got both eyes open, and that's not really true. It's certainly easier with two eyes, but it's not impossible to do with just one. And the reason for that is that the brain actually does a good bit of perception and allows us to make assumptions about the distances of certain objects. All right. So those three cues are listed here on the right-hand side of the screen. The first one is what we call retinal disparity. Now, remember, your retinas are the sensory receptors in the back of your eyeballs. All right. And this is binocular, so two eyes. All right. It's a binocular depth cue, referring to the fact that as the disparity between two retinal images of an object increases, the distance of the objects from us decreases. All right. So if you hold your hand right up in front of your face, all right, you can see just kind of a hand. But as you move it further, you see only part of it. As you move it further and further and further away from you, all right, your retinas are giving you two different images, and that allows you to calculate just how far your hand is from your eyeballs. There's also a linear perspective, which is a monocular depth cue, meaning one eye. And this refers to the fact that as parallel lines recede away from us, they appear to converge. All right, and I'll show you an example of this in the next slide. And the greater the distance, the more they seem to converge. This is sometimes referred to as perspective conversion. Interposition is another monocular depth cue, referring to the fact that if one object partially blocks our view of another, we perceive it as closer to us. Think about that. If somebody's standing behind a car on the other side of the street, all right, you know that the person is further away from you than the car is. All right, you can't see his waist and his legs. Therefore, he's behind the car. That means the car is closer to you. All right, and that principle of depth perception is referred to as interposition. You can find the relative distance of objects from you based on other objects in your field of view. Okay. Now, I told you that I would show you a picture, and this one is the linear perspective. All right. This is obviously an image of a set of railroad tracks, and if you look at this picture and look at the two red bars, if I ask you which red bar is larger, what are you going to tell me? Well, the quick answer would be that the one on top of the photo is larger, because you can see that image, or that red bar, is touching both of the rails of the railroad track, whereas the one on the bottom is just kind of hanging out in the middle of the bed of the tracks. Now, in reality, however, if you really look closely, you can see that the two objects are actually the same size. Those two red bars are exactly the same size. All right. It's just that the optical illusion that the railroad tracks are converging in the distance makes the top bar seem larger than the second. The same thing is true for the picture on the right. All right. There are three guys leaning up against the wall. The first guy is a dwarf, and the last guy is a giant, right? Wrong. In reality, all three of those silhouettes are exactly the same size. The one in the back looks bigger because of the converging lines that you see on all four sides of this image. Okay, so my friends, that is the end of the first video that of two on how we make sense of what we see. And I hope you learned something.